So today we are going to discuss first what is initial value problem, initial value problems. And then we shall discuss further a couple of more solutions of first order ODEs. We'll discuss exact equations and homogeneous exact ODEs, in fact, not exact equations, exact sorry, homogeneous equations or homogeneous ODEs. Okay, what is an initial value problem? In short, we write it IVP, means initial value problem. Initial value problems are basically, if we define it, first order initial value problems. First order initial value problem. Okay. First order initial value problem has one equation, first order differential equation, first order ODE. For example, dy by dx is equal to f of x y. This is the first order ODE. We define it along with another condition y of 0 is equal to some constant, maybe alpha. Now, as you know, differential equations, they do have a domain. So x maybe belongs to from A to B. Okay. Then here, you should have the first value of x. Okay, if it starts from 0 to some, if it starts from 0 to maybe infinity, then the initial value of the x is 0. So we define a condition at the initial value of this independent variable. Y at 0 is equal to some constant. Or in this case, y at a is equal to some constant alpha. Okay, we define equation along with a condition at the initial value of the domain variable. For example, here the domain variable, independent variable is x from a to b. Then the first value or initial value of x is a. So we define a condition y at x equal to a is equal to alpha. And for example, if x is between 0 and infinity, then the initial value of x is 0. So we define y at 0 is equal to alpha. So this complete problem, along with a single, this or this, along with a condition, it is called initial value problem. Now, why do we need to define this condition along with this ODE, ordinary differential equation of first order? As you know, the first order ODEs, their solutions are one parameter family of solutions. Okay, the solutions are, in fact, g of x, y, c is equal to 0. It's what it is, one parameter family of solution. It contains one constant, one parameter. Okay. In the presence of this parameter, I told you in the previous lecture that we have infinite many solutions. Okay. I showed you a graph as well, and a differential equation. If it has a one parameter family of solution, then it has infinite many solutions for every value of the c. This parameter c, it usually belongs to the set of real numbers. Now, we have infinite many solutions. We have one equation and we have infinite many solutions. Now, for example, if we are working on some practical problem, as I told you, the coffee problem. Okay, temperature of the coffee is decreasing, okay, by using Newton law of cooling. I told you that problem. Sorry, I hope you remember. So for that Newton law of cooling, we define a problem of this kind: d over dt is equal to some constant times t minus Tm, where Tm is some constant, which is the surrounding temperature or the room temperature of that cup of coffee. We also define another condition that at t is equal to 0 means at the initial time, the temperature of the coffee is 100 degrees, maybe Celsius or Fahrenheit. Now, this equation along with this condition, and this condition is called initial condition. Okay. Now, this condition will help us to find the constant of integration which arise due to the integration of this equation. Okay, while finding the solution, for example, by using separation of variables, you separate the variables and then you integrate both terms, both sides of this equation. You get a parameter constant of integration in the solution of this differential equation. Now, in the presence of that constant, we'll have infinite many solutions. We don't need infinite many solutions. We need only one solution. Okay, that suits our situation, our problem, our practical problem. So in order to find that unknown constant, which suits our situation, our environment, okay, this initial condition helps us to find that unknown parameter in the solution of this differential equation. Okay, so that is why we need an extra condition, which is usually defined at the initial time or the starting time of that physical phenomena. Okay, it could be in the middle as well. Okay, we can measure the temperature of coffee after maybe 2 minutes. Then T is equal to 2, temperature at T is equal to 2 minutes could be maybe 90 degrees. Okay, that temperature would constantly be decreasing. Okay, and will eventually it will match with the room temperature if the room temperature is constant. So, but it is basically recommended to, or it is in order to get accurate solution, okay, which is valid from the starting point to the ending point. Okay, we define condition at the initial time. Okay, this condition, as I told you, we can define it at in the middle as well in order to find the constant, but usually it is very easy to find the condition at the initial time. Okay, so this condition helps us to find that constant. For example, if we solve this problem by separating the variables, where K is the constant of proportionality here, okay, and K is basically heat capacity, okay, and that depends on the material of the body, whose temperature you are trying to measure, how it will go down with time. So this K is fixed for different materials. The coffee or tea is, if you are working with the tea, then tea is just like a water. So heat capacity of the water is defined. That is fixed. It is being computed by the experimental physicists, and that is I don't remember its exact value, but it is something like 1.4. I don't know, but you can see it's the value of K, okay, on Google. So if we choose this k for the cup of tea, then by separating the variables t minus tm, dt is equal to k times dt. Okay. Again, tm is another known constant, which is the room temperature. We assume that the room temperature normally is 30 degrees. Okay. Now integrating both sides, we can have 1 over t minus 30 degree dt is equal to k is 0.14 dt. Okay, now this is what it is, natural log of t minus 30 degree is equal to 0.14 t plus c. Now this is what we obtain, t minus 30 is equal to 0.14 t plus c. Sorry, this will go when we take the log on the other side, it will go in the power of the exponential plus c. Okay, now this is e t into e raised to c. This is another constant, we call it c naught maybe. So it becomes c naught e raised power 0.14 t. And here we have t minus 30. So t of t is what? It is 30 plus c naught e raised power 0.4 t. Now, here is our solution. Okay, here is our solution. But remember that k, here we have k should be negative here. K should be negative here. Okay. If it is negative, we have negative here, we have negative here, we have negative, 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 and then negative, because the temperature is decreasing. Okay. If the temperature is decreasing, we have to put here a negative sign, or the k should be negative. So this is our solution. Now at t is equal to 0, the temperature is what? It is something, initial temperature is 100 degree. By inserting this t, this is what? This is the value of t, small t, which is time, and this is the value of capital T. So at t is equal to 0, so what do we get? It is 100 is equal to 30 plus c naught e raised power 0. From here, we get the value of c naught, which is 70 degree, in fact, or whatever. Now we get the value of c naught. So our complete solution is what? It is 30 plus 70 e raised power minus 0.14 t. So this is your solution. Now you can compute the temperature of that cup of tea at any time. Okay. But notice that when t approaches to infinity, when t approaches to infinity, if you take limit on both sides, you can take here it as when t goes to infinity, limit t goes to infinity on t of t is equal to limit t approaches to infinity. Your solution is what? It is 30 plus 70 e raised power negative 0.14 t. Okay, this is what we have. We applied limit on both sides. Now the limit doesn't apply on constants. It remains 30 plus 70. So here only we can apply the limit t approaches to infinity e raised power negative 0.14 t. Okay. Now this limit is what? Anyone can anyone tell me?
0.
Why is it 0?
because e raised to power negative infinity will be 1 over e raised to power infinity, and it will be 0.
Yes, this limit is basically equal to 0 because e raised power negative infinity is 0. Okay. I hope you have studied these things in calculus 1. So what do we left with? It is limit t approaches to infinity t of t. Okay. Now, when t goes to infinity, capital T is equal to 30. What does it mean? Eventually, when t is approaching towards infinity, the temperature is approaching towards 30. Okay. So this infinity is not too much large. Okay. This after maybe 5 minutes, maybe 10 minutes, the temperature of T will coincide with the surrounding temperature. This T is not very big number. Infinity in different situations is different. Okay, I hope you know it. In calculus, you have studied these things. If you have any question, you can ask me. So if you don't have any question, the purpose of doing this example is to show you that why do we need an extra condition along with the first order differential equation? Okay, because that extra condition help us to find the complete solution or the particular solution. Okay, that particular solution that suits your situation. Okay, so as in this problem, if you are working on a problem where the temperature of a cup of tea is decreasing, then we'll have infinite many solutions, but the solution which matches our situation or physical problem, that is basically we can find that solution by defining an extra condition at the initial time. This gives us basically our the particular solution which suits our situation. In some situation, we are also not given this constant k. If this constant k is again not given, then we need another condition, maybe t at some 2. T at 2 is some constant, maybe 50. At some other instant also, we are given some other condition. That other condition help us to find this value of the other unknown constant. Okay. If I say you to solve this problem where k is unknown and tm is maybe 30 again, or any other constant, we are given two conditions. Now, obviously, this is initial condition which we use in order to find that unknown parameter which arise due to the integration. Okay, the other condition is given to find this unknown constant k, which arise due to the proportionality of these two things. Okay, so now repeat this problem. You are not given k. Find that k with the help of this condition, okay, and find that constant c with this condition, and then repeat this problem. Try to find the solution or the temperature of this phenomena, whatever it is. Okay. I hope you get it. If you have any question, you can ask me. Now, this was first order initial value problem. Now, if we have second order initial value problem, we'll definitely have two unknown constants, two unknown parameters in the solution of that second order boundary value, second order initial value problem. Now, the second order IVP. we can usually define it as d square y by dx square. It is f of x, y, and y dash. Okay, this is the general form of the second order differential equation. Now the solution of this differential equation may be g of x, y, c1 and c2. It must involve two unknown parameters because we have a second order derivative in this equation, and in order to reach at y, we have to reverse the derivative 2 times. So which will give us two parameters or the two constants of integration. In order to find these two constants, we need two initial conditions. Now, two initial conditions. At initial time, we can define only one condition on displacement function. Okay? If you look at physically at this problem, then y is what? Y is a displacement variable. Okay, we can only define only one initial condition on the displacement variable, when this phenomena has been started. Now the other condition cannot be defined at t is equal to 0. The other condition could be defined at the y dash, which is the velocity of or rate of change of that phenomena, okay, at the starting point. So the initial conditions we define along with this differential equation. We have now initial conditions. One is at if the domain is f(x) from a to b of this differential equation, then the initial condition is a. Then y at a is some alpha 1 and y dash at a is some alpha 2, some other constant. Okay. Now, this complete problem, along with two initial conditions which help us to find those two unknown parameters, is basically called an initial value problem of second order. Okay. Now, in order to implement this initial condition, if you get the solution, then you can apply this condition by taking x equal to a and y is equal to alpha 1 in this solution. In order to apply the second initial condition, first you have to take the derivative of the solution function with respect to x in order to get y dash. Okay. And then you can implement this initial condition. Okay. We'll do a couple of problems later on where we shall apply this initial condition on the derivative of the solution function. Okay. इसका derivative लेंगे तो आपके पास g dash times क्या आएगा? If you take the derivative of this function with respect to x, then g dash x y c1 sorry c1 c2 times y dash dy by dx. x का तो हो जाएगा ना, y का जब भी वेरिएबल आएगा यहाँ पे तो उसमें साथ में डेरिवेटिव आएगा y dash, ठीक है, or whatever you'll see when we'll do some examples of this. So this is a second order initial value problem. We can generalize this thing and we can define nth order initial value problem. In the nth order initial value problem, the equation should be of this form: dny by dxn is equal to f of x, y, y dash, so on, and y up to n minus 1th dash, because the nth derivative goes on the left hand side. Now, the solution of this differential equation involves how many constants? N constants: x, y, c1, c2, so on, cn is equal to 0. Now, how many initial conditions do we need here in order to compute the values of these n constants, n parameters? We need n initial conditions. starting from y at a is equal to maybe alpha 1, y dash at a is equal to alpha 2, and so on, and so on. Y n minus 1 dash at a is equal to alpha n. Okay, we need n initial conditions in order to solve this initial value problem. So this differential equation along with n initial conditions is called nth order initial value problem. Okay. If you have any question, you can ask. Let's do an example of the second order initial value problem, and then we'll move forward. Two. Okay. Example. For example, if we have y double dash plus 16y is equal to maybe 0, okay, then the solution of this differential equation is y at x is equal to c1 sine 4t, no, 4x, not t. For x plus c2 cosine of 4x. This is the solution of this differential equation. We are not still discussing how to solve this. This is a differential equation. I know its solution will be this. Okay. You assume that this is the solution. Now it involves two parameters, C1 and C2. Okay, and we are given two initial conditions, y dash at 0 is 0 and y dash at 0 is maybe 1. Okay. The first one is not y dash. It's y at 0 is equal to 0. We are given two initial conditions. Now, in order to apply the first initial condition, we can just put x equal to 0, y is equal to 0. Okay. At y is equal to 0 is equal to 0. This gives us 0 is equal to c1 sine of 0 plus c2 cosine of 4. Okay. Or you can define cos of 0, not 4. 4 times 0, it is cos of 0. Okay. Now we know that sine 0 is 0 and cosine 0 is 1. So it gives us C2 is equal to 0. Now, in order to apply the second condition, what do we need? We need the derivative of this function. So we take y dash of x is equal to just sine C1, derivative of sine 4x is cosine 4x times 4 plus derivative of this thing is C2 negative sine 4x times 4. Okay. यहाँ पे प्लस कर दें, यहाँ पे माइनस कर दें. Same thing. Now you have the derivative of the solution function. Now you can apply this condition, which is basically y dash at 0 is equal to 1. This gives us, you put x equal to 0 and y dash is equal to 1. Okay, so this gives us 1 is equal to c1 4 cosine of 0 plus minus c2 sine of 0 times 4. So here sine 0 goes to 0 and cosine of 0 goes to 1. So we get 4c1 is equal to 1. So c1 is equal to 1 by 4. This is your value of the other constant. Now inserting back these two constant values here, we get the solution y of x is equal to c1 is 1 by 4 sine 4x plus c2 is 0. So we get this solution, which is a particular solution. I told you what is a particular solution. A particular solution is a solution which can be obtained from the general solution, which involves the parameters in the family of solutions. Okay. By inserting some specific values of these constants, we can obtain a particular solution of the given differential equation. So this is the particular solution of that. If I say you y is equal to 0 is another solution of this differential equation, then what kind of solution is this? Y is equal to 0. Anyone? Can you tell me?
Trivial solution. Singular solution.
Trivial solution. Yes, it is another kind of solution as well. What kind is that?
Singular solution.
Yes, singular solution. Because a solution which cannot be obtained. Is it singular solution? Can we obtain this solution from the general solution by putting some specific values of C1 and C2?
No.
Huh? Remember that C1 and C2, they belong to R. Now, can we choose both C1 and C2 0? Yes, we can obtain. We can put them C1, C2 is equal to 0. So y is equal to 0 is not a singular solution. Y is equal to 0 can be obtained from the general solution by putting some specific values to the constant C1 and C2. So it is not singular solution. It is only the trivial solution. Okay. I hope you get it. If you have any question, you can ask me. You got this thing? Y is equal to 0 is the trivial solution. And it is particular solution as well, not a singular solution. Okay, it is another particular solution of the given differential equation. It is not singular. A singular solution is a solution which cannot be obtained from the general solution by taking some specific values of the constants. You remember this. I hope you get it. If you have any question, you can ask me. The next thing which we are going to discuss is the homogeneous ODEs. Okay. In order to discuss homogeneous differential equations, first order differential equations or whatever, first we need to discuss what is the homogeneous function. Sometimes homogeneous functions. A function f of x, y of two variables, which contains two variables, x and y, is said to be homogeneous if it satisfies the following property. F of tx ty is equal to t power alpha f of x y. This one. What does this mean? In fact, if we have a function f of x y, we'll call it homogeneous if we replace x by tx and y by ty in that function, and we can take t common outside this function, t some power of t maybe. Okay, t power alpha. Alpha could be any real number. Okay, alpha could be any real number. Let's see an example. For example, f of x, y, maybe it is x cube plus x, y square. Okay. Now, if we replace x by tx, replace x by tx and y by ty. Okay. At every instance of this function. So it becomes f of tx, f ty is equal to, we have x cubed means tx whole cube plus x means tx and y is ty whole square. Now can we take, now here it is t cube x cube plus t cube x y square. Can we take t cube common out of this function? It is x cube plus x y square. Now x cube plus x y square is what? It is the same function f of x y. So it is t cube f of x y. Okay. By replacing x by tx and y by ty, if we can take t common out of each term, and we are left with the original function where we have started, then this function is called homogeneous. This is called homogeneous function. Okay.
Sure.
Yes.
Didn't we say that homogeneous functions are those where the function in an nth order differential equation was zero?
Can you repeat, please, your question?
Like in the previous lectures, we studied that homogeneous equations are those where like the function of x was zero.
Yes, yes.
Or is this something else?
That was homogeneous differential equations. Now we are talking about homogeneous functions. These two things are different. Okay. These two things are different. Homogeneous functions, basically, they tell us that the degree in each term of that function is same. Degree. Now, this function has two terms, one term and the second term. You can add up the degree. Here, the degree of x is 1, degree of y is 2. Here, the degree of x is 3. In each term, the degree of variables is same. This is what we are looking for here. If the degree in these two terms is not same, then this function will not be homogeneous. For example, if I say that this is the function x cubed plus xy, then what is the degree in the first term? It is 3. And what is the degree in the second term? It is 2. Then we cannot have t common out of each term, and we cannot obtain the original function after replacing x by tx and y by ty. Okay. So the functions, यहाँ पे अगर x y है, तो यहाँ पे ये 2 नहीं आएगा, और फिर यहाँ पे t और t क्या आ जाएगा? t square आ जाएगा. यहाँ पे you cannot take t cube common. Okay, you can take only t square common. T square common आएगा, यहाँ पे एक t आ जाएगा. Okay, so this is not equal to t square f of xy, because here this function is different from the original function. Okay, so this function is not homogeneous in this case. Now, कुछ ट्रिग्नोमेट्रिक फंक्शंस जो है वो इन होमोजेनस इक्वेशंस में नहीं आए, ठीक है, क्योंकि उसकी डिग्री वी डोंट नो exactly the degree of that function. That is a non-linear function. Who is asking me the question? Are you clear with these things? Who was asking me the question?
Yes, sir.
Talk to me. What was your question? Please tell me.
I just have the confusion between homogeneous function and equation.
Homogeneous ODEs, they are different thing, and homogeneous functions are different things. Okay. One thing which we also see in homogeneous ODEs is that we did an example here of second order ODE. If an ODE, एक तो हमने example, एक तो हमने कहा था कि अगर हमारे पास nth order, if we have an nth order linear ODE whose right hand side is non-zero, f of x, then that equation is non-homogeneous. If the right hand side is zero, then the equation will be homogeneous. Okay? That is the proper definition of homogeneous and non-homogeneous ODEs of nth order or whatever the order of that differential equation is. Now, this equation, according to that criteria, is homogeneous differential equation. It has nothing to do with the homogeneous functions. Okay? We are not checking the degree of that function in each term. We just see at the right hand side, if the right hand side is zero, then it is homogeneous differential equation of second order. But what if I write here what if I write here y double dash plus 16y plus maybe 3 is equal to 0 or 3x squared? Is this homogeneous second order ODE? You tell me who was asking the question.
Yeah, it's not.
It's not homogeneous. Why?
Because of the 3x squared.
Because this term doesn't involve y. Okay. On the nth order linear differential equation, on the left hand side we have y in each term, but in this term we don't have y in this term. But in fact, this term should be here. It should be on the right hand side because it doesn't involve any y. Okay. Now, in order to avoid this confusion, I give you a simple trick. Homogeneous differential equations, if it is homogeneous, we need to check whether it is homogeneous or not. Homogeneous ODEs, they must have trivial solution. Okay, y is equal to 0 must be the solution of that differential equation. Then it is homogeneous differential equation. Okay, now you can see that this equation has this y is equal to 0 solution, because if we put y is equal to 0 here, the equation is satisfied. We get 0 is equal to 0. But if you put y is equal to 0 in this equation, you will not get y is equal to 0 is equal to 0. It is not homogeneous because trivial solution doesn't satisfy this differential equation. If a trivial solution satisfies any given differential equation, then that differential equation is homogeneous differential equation. Okay? Whereas homogeneous functions are different. In homogeneous functions, we look for the degree of variables in each term. Okay? If the degree in each term is same, then the function is homogeneous. Okay? Now, previously when we had 2 here, we had 2 here, we had 2 here, we had 3 here, we had t, yahan pe 3, yahan pe 3. Then this function is homogeneous because every term in this function has same degree. And this f is called is homogeneous function function of degree 3, because in each term the degree of the variables is 3. Okay, this is homogeneous function of degree 3. I hope you get it. If you have any question, you can ask me. Another example of this homogeneous thing is now you can, I hope you can tell me whether the function is homogeneous or not by just looking at the function x squared plus xy plus 1. Is this homogeneous? Is this homogeneous function?
No, it is not.
Oh, sorry, it is.
No, it is not, because here the degree of the variables is what? The degree of the variables is
0.
not 0,
Sorry,
not 1.
0.
Okay, because here you can write this thing as xy power 0 or x power 0, y power 0. Okay, the degree of the variable is 0. So this function is not homogeneous because in each term the degree is not same. So this function is not homogeneous. I hope you get it. Now let's start with the solution of homogeneous equation. Homogeneous ODEs or homogeneous equations. Let me fix it. Homogeneous first order ODEs or homogeneous equations in general, we say them. A first order ODE of this form mxy dx plus nxy dy equal to 0. We call it equation 1. Now this could be the form of first order differential equation where m of xy is some function of xy. It is basically the coefficient of dx, and n of xy is the coefficient of dy is equal to 0. If we simplify it, we will simply get first order ODE. Okay. How can we obtain first order ODE from here? We take this thing on the right hand side and we divide it. Here we get negative n over m. Huh? नहीं हाँ ठीक है नहीं m ऊपर आएगा n नीचे आएगा क्योंकि dy का कोएफिशिएंट डिवाइड होगा ना m over n, where m is a function of xy and n is a function of xy. As a whole, this function is what? It is a function of xy. So what do we get? We get the first order ODE. Okay. So if we have this differential equation, then where m of xy is a function of xy and n of xy is a function of xy, we have two variables. Now we check whether this m and n, they are homogeneous functions or not. If they are homogeneous functions, then we can solve it by using homogeneous technique. Okay, if these two functions are homogeneous functions of same degree, okay, homogeneous functions of same degree. So what do we need to check here? Two things. These two functions are homogeneous, and second thing is their degree is same. Okay? If these two things are true, then we can solve it by using the homogeneous equations technique. How do we check whether these two functions are homogeneous or not? What do we check? We check whether by replacing x by tx, x by tx, and y by ty. So we should get t power sum alpha times m of xy. Similarly, for n of tx and n of ty should be t power alpha n of xy. Okay, this alpha and alpha should be same. Okay, if it is same, then we say that these coefficient functions, they are homogeneous and their degree is identical. Then how to solve it? How to solve it after checking these two things? Then the next question is how to solve it. We assume that the solution is of this kind. We assume that the solution of ODE 1 is of this type. What it is, y of x is equal to u of x times x. Okay. Where u of x is some unknown function. Okay, where u of x is some unknown function. Now we assume that this solution is of this type. Okay. If this is the solution, then insert this solution into the given ODE. Okay. Insert or substitute 2 in 1. Okay. This will convert the ODE 1 into a separable ODE. Which then we can solve by separating the variables. Okay. Let's do this thing with the help of an example. Yes, this one. Example. Solve the following ODE. X squared plus y squared dx plus x squared minus xy dy is equal to 0. Okay. Now, by looking at the coefficients of dx and dy, I can judge this is homogeneous function because the degree in each term is same. The degree in each term is same. So these two are homogeneous. Okay. As you just write it over here, m of xy is what? It is x squared plus y squared, and n of xy is what? X squared minus xy. Okay. Now, m of tx ty is equal to t squared. You can say here I can directly write, you have to check it, m of x, y, and n of tx, tx, ty is again t squared n of x, y. Okay, this implies m and n are homogeneous functions. Therefore, okay, this is the first step. Step one. In order to solve this homogeneous ODE. The step two is what? Step two is you assume that y is equal to u of x times x. Okay, you call it one and you call it two. Okay. Now inserting two into one, what do we get? X squared remains x squared. We only insert y is equal to ux. Okay, x will remain x. Yeah. It's similar kind of concept. Here we inserted x by tx and y by ty, but here only we are replacing y. So we get u square x square dx plus x square minus x into ux, okay, into dy equal to 0. Now here you can see that we can take common x squared throughout this equation, okay, from the both terms. So from here, x squared, you can take common. What do we get? 1 plus u squared. That's one more thing. We have to convert dy as well, okay? Because if you are putting y is equal to this, you are trying to convert y into a new variable u, okay? Then if y is this, then what would be dy? You just take the derivative with respect to x, okay? So it would, what do we have here? We apply the product rule. The product rule, according to product rule, derivative of x is 1, u remains as, plus x as it, and derivative of u is du, okay? Because dy is here. So we also insert 3 here instead of y, dy. Here you have x here common, so we get 1 minus u times here u plus x du is equal to 0. यहाँ पे आपके पास dx भी आएगा ना, हाँ यहाँ पे dx. Okay. Now this x square can be eliminated. Okay, this x square will be eliminated. We can put it equal to 0. This equation, what do we get here now? 1 plus u square dx plus 1 minus u times u plus x du equal to 0. Now this equation has been transformed, the original equation has been transformed into two new variables, x and u. Okay. Now, if you further simplify it, you would be able to see that this equation is a separable first order ODE. You try to separate the variables x and u and then solve it. Once you solve it, you'll get u of x. After solving this separable ODE, you'll get u of x, the solution. If you get u of x, then by inserting back u of x here, you get the y of x, which is the solution of the original given differential equation. Okay. Now let's try to solve this differential equation. This is again first order differential equation. I hope, let me write it somewhere here.
Wait, sir, I have a question.
G.
In the जो आपने पहले लिखा था, when you were finding dy, shouldn't that equal u dx plus x du? ये जो last line,
ये बोला?
हाँ इसके नीचे, हाँ वही उसके
हाँ,
नीचे जो आपने dy लिखा है, shouldn't this be u dx plus x du?
You're trying to apply here the product rule. You're taking the differential of y. The differential of y is what? With respect to x, you are taking derivative with respect to x. So here it should be dxu. Yes, you're right. So it is u dx, not only u. Thank you. So it should be here u dx. Good. Thank you. It should be u dx because we are taking differentials. Okay, if you are taking differentials, then here we have x power 1. Derivative of x power 1 is 1, and then you take the dx as well. So it should be dx. Thank you. So we are going to write over here now again the equation 1 plus u square dx plus 1 minus u times u dx plus x du is equal to 0. This thing. But remember one thing. If you have some, we already define it into u times x. So it will always be this thing. If you have some other power of x here, for example, x power 2, then it will be 2x dx. Okay, because the derivative independent variable is x. So we take the derivative. So we always get this thing here. Now separating variables, we try to separate the variables here. So this term, for the time being, we write it in the same way, and this will give us u dx plus x du minus u square dx minus x u du equal to 0. Now you combine the terms with dx, and it is 1 plus u square plus u minus u square dx, and then you combine the terms with du. So it is this and this. It becomes x minus xu times du is equal to 0. So here, what do we get? We cancel these two things, and we are left with 1 plus u dx plus, we can take common x from here. So it is x1 minus u du is equal to 0. Now you can see that this differential equation is separable. You can separate the variables. You take this thing on the other side and divide 1 by 1 plus u. So it is 1 minus u du is equal to 1 plus u dx. Okay. Now you divide this thing on the left hand side and you divide x on the right hand side. Minus. Thank you. Will be minus here. So what do we get here? 1 minus u over 1 plus u is equal to negative 1 over x dx. Okay. Here we must have du as well. Okay. Now we'll solve this thing. How to solve it? You apply integration on both sides. You take the integral 1 minus u over 1 plus u. Du is equal to negative 1 over x dx plus constant of integration, which is the pyramid. Now, I hope you can solve it. Can you do this integration?
ln of u minus u.
ln of u minus u. कैसे भाई?
Oh, actually, no.
No.
Yeah.
If you have two polynomials of same degree in a
So
fraction,
we can use partial fraction to solve.
partial fraction, yes, partial fraction, but first you have to divide it. Because if you have two polynomials in the numerator and denominator of the same degree, then you have to divide this thing with this thing first. I hope you know it. Try to integrate it. If you can't, you can ask me in the next lecture. I'll help you, or you can ask the TA. Using division, I can write it. Using division, I can write this thing as -1 plus 2 over 1 plus u. Okay, the integral of this thing is negative of log x plus c. Okay, and sometimes in order to simplify our calculations, I can write the constant as well, log c. Okay, I hope you know these things. So the integral of this thing is now negative u plus 2 times natural log of 1 plus u. Sorry, is equal to negative natural log of x. You put a mod here, unless you know x is always greater than 0, plus some constant c. We don't need it. So after simplifying this, you can have the value of u here and try to solve it. Otherwise, its solution is given in the notes. You can see it from there. Okay. So once you have the solution, then you can put y is equal to ux, and u is what? You have to eliminate u from here in order to get the solution in x and y, because the original equation is in x and y. The solution should be in x and y. Either you find u from here in terms of x and then put the value of u is equal to y is equal to ux, put the value of u in that y is equal to u times x, or there's another method of this thing, y is equal to ux. This implies u is equal to y by x. Okay. So if you cannot separate u from here, you just put u is equal to y by x in this solution. Here, if you put u is equal to y by x, y by x, y by x. So you get the solution in terms of x and y, which is the solution of the original differential equation.
Sir, does the substitution always work? जब ये इस तरह की form में हो?
Yes.
M of x and y and then n of x and y.
Only for homogeneous differential equations. Okay. Homogeneous first order ODEs, only for this. Now, why is it so? Why we assume this solution? It's a technique. It doesn't have to be any thing to which has any kind of physics involved in this thing. There's no physics behind it. It's just a technique. Okay? The person who invented it first time, he might have continuously thinking for months or maybe years in order to invent this solution. Because it's a technique. It's a technique of converting an equation into another kind of separable equation, which then can be solved. I told you, solving linear and linear is something simple, but solving non-linear differential equations is it's very difficult. You have to think very long time in order to find the solutions of non-linear differential equations. Okay, because this is a kind of non-linear differential equation. Okay, because it involves y squared. So ये जो भी टेक्निक यहाँ पे हम पढ़ते हैं इनको इन्वेंट करने के लिए, because it's a hit and trial method. You just think what is happening, you try to find some way by any mean to get the solution. Okay, so this thing has nothing to do with the physics, with any concept. It's just a technique of converting an equation into another equation, which is solvable luckily. Okay, it might be converted into some other equation which also doesn't have any solution or any method to solve that different equation. Okay. So luckily, this method has been invented by some mathematician, or it's not necessary that the mathematician might have given this technique. It may be some physicist, it's maybe some other kind of man who might have given this procedure of solving this differential equation. क्योंकि बहुत सारा मैथमेटिक्स जो है वो अनरेफरेंस्ड है, ठीक है। ज्यादातर मैथमेटिक्स जो हम डेली लाइफ में आजकल देख रहे हैं, जितना भी मैथमेटिक्स है, that was documented by Euler. Euler is a French mathematician. So before that बहुत सारी जंगें हुई थी, मंगोज एंड तातारीज जो हैं, उन्होंने जो डिस्ट्रॉय कर दिया था सारा कुछ, ठीक है। वी हैड लॉस्ट लॉट ऑफ लिटरेचर, मुस्लिम लिटरेचर, ठीक है। उन्होंने बगदाद, इराक, जो जो बड़ी बड़ी लाइब्रेरीज थी इजिप्ट में या बगदाद में, वो बहुत सारी उन्होंने डिस्ट्रॉय कर दी थी, आग लगा दी थी उन्होंने। बाद में ये आयलर मैथमेटिशियन था, फ्रेंच मैथमेटिशियन, उसने सारी चीजें इकट्ठी करके he documented more than 90% of the mathematics which we see these days. Okay. So thanks to Euler that he saved this technique. Okay. If you have any question, you can ask me. No questions? Look at page 7 of my notes as well. G. Zainul Abedin. You have raised a hand. You can ask me questions.
Sir, can you please upload the recording for Tuesday's lecture?
Okay, I'll record it. Well, mistakenly, I pressed the button of record on this computer. Okay, last time. तो वो इस कंप्यूटर पे सेव होगी. I thought कि वो मैंने प्रेस किया है record on cloud. अगर record on cloud होता है ना, तो वो फिर मेरे लॉगिन में अपने लैपटॉप से खोल के डाउनलोड करके तो अपलोड कर देता हूँ. तो लास्ट टाइम mistakenly I pressed record on this computer. अब इसी कंप्यूटर पे रिकॉर्डिंग पड़ेगी. I'll try to copy it today. I don't have USB right now with me. I'll go to my office and find USB key. I'll come back here, copy, and then I'll upload the previous lecture. But don't worry, today's lecture is being recorded on cloud. If you don't have any questions, let us see another possibility of this homogeneous ODEs. Another example of homogeneous, negative y dx plus x plus square root of x y dy equal to 0. Now, let me turn it off. Now, this equation, here we have y, its degree is 1 in this whole term, its degree is 1. Here you have degree what? 1 square root, 2 square root. It is in fact 1 again. But this we cannot do in homogeneous equations. This is, we can only do this thing in for the homogeneous functions. यहाँ पे भी degree 1 है as a whole because its degree is 2, but when we take square root, the degree becomes 1. Okay. Instead of assuming solution y is equal to ux, okay, we can reverse the substitution as well. We can assume x is equal to uy as well. But in order to change the notation, you just put y is equal to x equal to vy, where v is a function of y. No. Okay. So v is a function of y here. Now, whenever you take dx, it would become v dy plus y dv.
So how do you know which one to do?
It's your choice.
So both work?
Yes, both works.
Okay.
Okay. Either you substitute this one or this one. Okay. Whatever seems easy to insert in that equation. Okay. अगर एक से insert करने से आपकी simplifications नहीं हो रही, बहुत जल्दी मुश्किल हो रही है, तो आप दूसरी put करके check करते हैं. ठीक है. On the other way, both works. It depends what kind of functions are they, and if you feel comfortable with this substitution, you can use this one in some particular equation. So I hope you can do it with this substitution as well. This example is given in here in my notes. You can see it. We didn't do this in LA. This is new thing. LA में homogeneous किया था ये वाला.
So we did them with certain
Yes, we did.
all of them.
चलो ठीक. Okay, because there are many students who might not have taken LA before taking this course. Are there any students? It's a prerequisite. LA? Calculus is, I think, prerequisite of this course. Can anyone tell me what is the prereq of this course? If it is LA, then we are. Chale, कोई बात नहीं. Nobody is interested.
So it is LA, I just said.
Oh, boom. If it is LA, then why we are doing these things? We are repeating these things.
Yeah, because like the last week of LA, we did all of these differential equations.
So we pretty much had to do just book say.
Okay, if you have any question, you can ask me. Otherwise, we are going to stop it here today. In the next lecture, I shall go a bit fast when we'll discuss exact equations and non-exact equations. I hope you have already studied those equations in LA MATH210. If you have any question, you can ask me. Otherwise, I'm going to stop this lecture. See you next time, maybe, inshallah. In the next week, there will be a quiz. The quiz will have all these topics which we have studied in the previous lectures. In the first lecture, you would like to give the quiz in the first lecture or in the second lecture?
Second.
Okay.
Second.
Whatever.
But wait, do we not have Cal 2 quiz on like the second day as well?